We are Team 5, and we are working with MC Dean to build a BAS trainer. Our basic requirements were mostly set by MC Dean, which included the budget, how quick the failure should be detected, and the board side. For performance, we wanted to be able to interface with Niagara software. We want to have one floor of the building lighting system represented. We want it to take less than an hour for a professional engineer to understand. We want the system simulation response to be less than 20 seconds, and we want the trainer to simulate 3 different systems. For excitement, the trainer can be easily transportable. The system responds and alerts to deviations from set temperatures with plus or minus 5 degrees. The trainer is less than 50 pounds, and multiple floors of the building lighting system is represented.
Our final design is a 3-foot by 4-foot wooden board with a wooden outer frame and removable front and back boards for ease of use. The board is constructed using plywood for durability and ease of manufacturing. The board has a subsection dedicated to each building system being modeled, represented in our sketch using rectangular extrusions. All of the hardware for the board, such as PLCs, sensors, and building systems, are mounted on the front of the board, with wiring being run behind the board. Here is a 3D model of our design, showing the sensors, programmable logic controllers, and system subsections.
The type of controller we chose to use is a JACE. We chose a JACE without built-in inputs and outputs to simplify the wiring of the trainer. The controller will be connected to a power supply, the sensors and output devices, and a computer with Niagara software. Use of relay outputs will be prioritized for discrete 2-state devices which would only need switching on or off, like the lights. Analog outputs will be used for devices which utilize continuous signals.
For our preliminary design, the trainer component arrangement were inspired by the company Econex product. In the early stage, we considered to only simulate the HVAC and the lighting system of buildings our design. All components such as controller, sensors were connected through breadboards.
This is what we came up with for our second iteration. Both components of the trainer and the trainer compartments changed. Our team decided to include 3 systems, the boiler, the HVAC, and the lighting system. Instead of a breadboard, we added a PLC. We decided to use LED lights for each system to show if they were on or off. And we also added a fan and a humidity sensor for the HVAC system. Originally, everything was displayed on a board, but in this design, the trainer is enclosed in a case for ease of transportation.
So this is our system architecture. First, we have our HVAC system, which is subsystem 1. It starts with the temperature probe with heat going in and it's sending signal to the PLC. The PLC sends it back to the computer for it to gain a troubleshooting scenario. And the computer sends it back to the PLC, which then signals the DTD to turn the fan or the heating coil on or off. Our second system, which is the lighting system, starts with the light sensor, which sends signal to the PLC, then back to the computer, back to the PLC, then turning on or off the lighting LEDs. Lastly, we have our boiler system, which starts with a computer with code going in, sending signal to the PLC, and then sending signals to turn on or off the boiler LED lights. For the HVAC system, in order to cover some of the functional requirements, our design parameters would be that the temperature probe would be able to detect temperatures between 32 and 131 Fahrenheit, and the DTD will be able to simulate varying fan speeds corresponding to desired temperatures, which will encompass our FRs. We will also have LED lights to represent the filter status and damper. In order to analyze the system, the temperature collected by the temperature probe will be recorded by the software, and the resulting fan speed and temperature of the heating coil will be controlled through that said software. Some of our risk was that the heating coil would reach alarmingly higher temperatures without supervision, possibly causing a fire. However, the team will make sure that there is somebody always watching the operation. And another risk was that the BAS trainer would be exposed to excessive heat, cold, or moisture, but we would have proper protection during travel and storage with that in consideration. For the analysis and design accomplishments of the HVAC system, some of our biggest considerations were deciding how we would detect the temperature and simulate heating and cooling. We first decided on having a computer fan and a separate heating coil, but after research we realized it would be better to have them combined into one, which is why we decided on the Delta training device. This option was presented to us by our vendor Zach. For temperature detection, we first were going to have a digital thermostat that the team would operate manually. However, MC Dean wanted a more realistic temperature detection, which is why the team decided on a temperature probe instead.
More details on Subsystem 2. The LED lights in our trainer represent multi-floor lighting system of a building. The lights will be controlled using PLC, which will receive input from occupancy sensor or input from the software directly. The lights will correspond to the signals. We identify some risks. To avoid damage of electronics component due to high voltage, we will use a transformer to convert down the voltage within 24 volts, and we will ensure the sensors are compatible with our software and controller. Then we will design a proper protection to avoid accidental impact. Those LEDs were set to connect in parallel circuit to represent and simulate general building system, and controlled by JACE and the Niagara software. Initially, a single label was only considered, but we want more, so we decided to include multiple LEDs to represent a multi-floor lighting system within a building. We also decided to integrate the LED lights into each building component, such as the boiler, the fans, as status indicator, and we found that LED can be easily connected to the JACE and programmed through Niagara. Picking out the best electronics product, we will consider the pricing, the performance level, and their efficiency.
Our next subsystem is the boiler. For our design parameters, we decided that the boiler system will include an ISO valve, the boiler status, and its temperature. The four components will be represented by LED lights on the board that correspond to the command input in the software. The Niagara software will run constant analysis of the board and the trainer. The software will also give daily summaries and reports about how the trainer is operating. So the risks are, for our high risk, desired or expected outputs may not occur due to programming issues and mistakes. Our medium risk is communication failure between simulation, lights, controller, and Niagara software. And our low risk is circuit shortcuts might lead to failure of the board's LED indicators. Originally, the boiler system was not included, but after discussing with our mentor, we added a boiler system. In our second design, we added a switch to turn the system off and on through the trainer. After our tour of the MC Dean facilities and discussion with our mentor, we decided to remove the switches and to control the boiler system through the software for ease of use. Also, during our visit, we decided to add indicators for the different components of the boiler system instead of only having one indicator for the entire system.
Our fourth subsystem, and only system without a physical component, is our software modeling. We'll be using Tritium's Niagara software to model each physical subsystem. Our objectives are to have each physical system graphically modeled in Niagara, for the system to perform data collection using attached sensors, and the software will interface with our electronic hardware to turn systems on and off and show the status of our components. Our biggest expected challenge with the software simulation is gaining expertise with our limited time. To counteract this, we will lean heavily on our mentors who have experience coding BAS systems until our team feels proficient with the software. At this stage, no analysis or design has been done using the software. The team is in the process of purchasing the necessary license and will begin the design process as soon as that happens. The software serves as our means of communication between the PLC, a JACE controller, and our sensors and outputs. The software interacts with our controls hardware using a similar architecture to the graphics shown. The model shown on the right is an example of how our system will be modeled on the Niagara software. Each system, lighting, boiler, and HVAC, will have key components modeled in the software. Each selectable component and action in the software will produce a physical output and provide feedback to the software system. The temperature sensor and occupancy sensor will also provide feedback to the system to determine the status of components.
We had concerns over the overall cost of the software and issues obtaining the software licensing, but we expect to obtain the software soon and can begin working on learning the software. We anticipate some shipping or lead time issues. Our team is also concerned about working with the circuitry and wiring of the trainer as we have limited experience in that area. We learned about working and communicating in a professional environment and how various aspects of that can affect a project. We also learned to avoid underestimating our deadlines. The team did not anticipate the amount of research required by us and our MCD mentor. This greatly affected our project timeline.